In this module from Chapter 4 on reproduction, Module 4.4, I cover what is referred to as event history charts that are used to visualize individual level reproduction in cohorts. The example I will show is reproduction in a 1,000 fly cohort of medflies. Consider a female fly that lives to age 10 days with her life course depicted as a horizontal line divided into segments according to age, and thus the length is proportional to the length of her total lifespan. Each of these age segments is color-coded according to the number of eggs she lays on that day. For example, day 0, she lays 0 eggs, and thus it is color-coded green. The next 2 days she continues to lay 0 eggs. They too are color-coded green. Then at age 3 days she lays between 1 and 30 eggs, and we color-code this level of egg laying in yellow. Likewise on day 4 her egg laying level is between 1 and 30 eggs, and then on day 5 she lays over 30 eggs and we color-code that red. We continue the color coding process through day 10 for this particular fly. We do this for 1,000 flies and rank order the resulting horizontal lifelines top to bottom from shortest lived to the longest lived, from which a cohort survival curve emerges. But because each age of these 1,000 flies is color-coded, it is possible to visualize the egg-laying patterns and intensities by age at the individual fly level as shown here. This example graphic for reproduction in 1,000 individual medflies contains a great deal of information. Note again that age is on the x-axis and number alive on the y-axis. Since the average individual in this 1,000 female cohort lived around 35 days and laid approximately 760 eggs each, on average, each figure depicts over 35,000 egg-laying days, representing the distribution of over 750,000 eggs. Because the graphs are constructed from original rather than smoothed or curve-fitted numbers, they allow the data to speak for themselves. This is important because abrupt changes in the level of reproduction between adjacent age classes, for example, 0 eggs laid at one age followed by 50 eggs laid at the next, appear in these graphs that would not appear in figures designed to show, for example, zones of high and low reproduction. Such subtle patterns and nuances can highlight both cohort and individual patterns. A broad pattern that is immediately evident in this chart is the sigmoidal shape of the cohort survival schedule, showing a gentle decrease from days 0 to 20 days, during which the first 100 flies died. This is followed by a more rapid drop from days 20 through 50, during which around 800 more flies died, and ending in a long tail at the oldest ages when the remaining 100 flies died. This pattern is a manifestation of an underlying mortality schedule in female medflies that accelerates at young and middle ages and decelerates at older ages. A number of other aspects of this figure merit comment. First, there is a weak correlation between the age of first reproduction and lifespan, which is apparent from the absence of any distinct trends between the leftmost band depicting pre-reproductive ages versus the lifespans depicted by the survival schedule. Second, although the figure shows that there are high egg production days throughout the cohort and across all ages, most reproduction is concentrated in a reproductive window spanning ages 5 to 25 days. This 20-day band of high egg production appears at nearly all longevity levels and thus implies that the correlation between the early reproduction and longevity is also weak. Third, high egg production days, that is the red-coded days, were noticeably absent from flies living beyond 40 days. Fourth, low levels of egg production were evident at several times during the life cycle, including during the first few days of oviposition and the last several days of life for each fly. During the oldest ages, see the survival tail, and also throughout the cohort as shown in the more or less even scatter of low egg production days at all ages across individuals. Fifth, of the 35,600 fly days in the cohort, a total of around 14,500 or 40% were days in which no eggs were laid. These zero production days can be classified into several types. The immature periods experienced by all flies prior to laying their first eggs. The zero production days resulting from lack of egg laying in sterile flies, as well as those zero production days due to day-to-day variation in egg laying by fertile flies. And the post-reproductive period immediately preceding death, as well as the low egg production at the cohort survival tail. The importance of individual level data. This analysis of patterns of reproduction across individuals and the graphical techniques that help visualize individual level data highlight several reasons why longitudinal data on individuals is preferred over data that is grouped or cross-sectional. First, as a study population ages, it becomes more and more selected owing to attrition. By 40 days, the fly population used in this illustration had less than half of the original cohort. The loss of individuals over time reveals that cohort means from measurement on young females are based on observations of flies that did not all survive to old age, while data from the older flies obviously represents a select subgroup of the population that did survive. Second, longitudinal data reveal the between fly variation in egg laying and thus reveals compositional influences on the cohort average. For example, individual level data show whether a decrease in cohort reproduction with age is due to an increase in the fraction of females that lay zero eggs or to an overall decrease in the level of egg laying by each individual. Third, if periods of more intense egg laying vary from fly to fly, this intra-individual variation can be wiped out in the process of averaging across individuals. For instance, the shape of the peak of egg laying in the averaged or cross-sectional egg laying display may not resemble any of the peaks observed in an individual's egg laying behavior. Fourth, longitudinal reproductive data on individuals is important because it allows between fly comparisons to be made on lifetime levels of reproduction and in turn on the long-term trajectory of reproduction in each individual over a specified period. In particular, it provides important insights into the reproductive age patterns of flies by comparing high versus low lifetime reproductive rates, early versus late ages of first reproduction, or short versus long lifetimes. This completes Module 4.4 on event history graphics for use in visualizing age reproductive patterns at the individual level.